All right, now we're going to move into air pressure. We've talked about temperature, we've brought in energy to the atmosphere. The next piece of the puzzle, shall we say, is air pressure. It's a variable, which means it changes. And you experienced that this week. You had a cold front pass your house, probably this week. Depending on where you live, we'll say that way. And when that cold front went through, the pressure dropped until it went by and then rose again. And that change in air pressure can be helped in forecasting what the future weather and what the weather is going to be. There are horizontal variations in air pressure and there are vertical variations in air pressure. So let's define what air pressure is. Well, I got to understand what a force is first. Have you ever thrown a baseball or a rock and you notice it moves? You applied a force to that. So a force is just a mass, which is what weight, not really, but it's a bunch of molecules in a place times an acceleration, how fast it's going. That's a force. Molecules always are exerting a force. They collide with other molecules. Molecules basically are always in motion. So the more they collide, the more molecules are together in a tighter spot, the more force is being generated. And this adds up to air pressure. It's a cumulative force of all these collisions. Dalton stated that each piece of the atmosphere, air type of air, in other words, nitrogen, oxygen, all have a pressure. And when you add those pressures up, they equal the total pressure. So it's just a weight. If you stepped on a scale, you have a weight. Well, the atmosphere stepped on a scale, it has a weight. It's mass times acceleration of gravity. So the average air pressure is about 14.7 pounds per square inch. So if you're standing outside, think about it. Every part of your body, or inside, wherever, is getting 14.7 pounds per square inch of weight on it all the time. The higher up in the atmosphere, that would be a lower number. Further down, if you went really, really underground, literally, you could get more weight. However, air is inside you, and it's in the structures you live in, like your house. So that is why we don't collapse under all this weight. And a way of measuring it was a barometer. Formerly, we used mercury barometers. However, mercury is kind of a hazardous material. Once we learned that, we have moved away from those barometers. But mercury was the first thing to use. What they did was they found a tube, took all the air pressure out of it, all the air out of it, basically, and then just plopped it right into the mercury, and the mercury just went right up that barometer, that tube. And those inches of mercury is one way we still measure the amount of air pressure. Here are different measurement pieces. Basically, you're going to hear me talk about millibars. Millibars is kind of a metric unit. It's related to pascals or kilopascals. And 1 inch of mercury is about 5.4 millimeters of mercury. And you can relate that literally to millibars. Air is compressible. What does that mean? Well, did you ever try to compress water when you're playing in the pool or out in the ocean? It squirts out your hand. Well, actually, you can compress air in your hand and pull it tighter. What that means is that the molecules above you in the atmosphere are all pushing the air down closer and closer to the surface. So there are more and more molecules of air the closer you get to the ground. If you went up in the mountains, I'll use an example. When I was in the Rockies last year in the summer, we went up to about 13,000 feet. And at that point, a significant part of the atmosphere is actually below me. And you could feel the wind blowing, but it didn't feel as strong. When you went down out of the Rockies, that same wind felt much stronger. That's because there was a whole lot less air molecules up there. So we have averaged through time vertical profiles of air pressure and temperature, and they're called the standard atmosphere. And they're done for different locations all over the globe, different seasons. And they're a means of relating the air pressure at a location well above sea level to what the actual sea level pressure is. They're not perfect because many days the atmosphere is not standard, but they can give you a quick approximation. Here is a horizontal variation in air pressure. When the air pressure gets lower, you tend to have stormy weather. When the air pressure gets higher, you tend to have nice weather. Notice, we'll say about 10, 12 millibars here, 10, 13 maybe. And here, the low pressure is 1,007 millibars. So that is a 6 millibar difference. Only 6. That is not a big pressure change. If you were to walk up the stairs, you might have 6 millibar pressure difference. So it doesn't take a lot in the horizontal to notice small differences in pressure that have major impacts on your weather. However, in the vertical, pressure changes much faster. So air temperature increases the kinetic energy. All right. So you would think, oh, well, where it's hotter, everything's going to have a higher pressure, right? Well, the atmosphere is not a closed container, as it points out here. So density changes. What that means is the faster these molecules move together, the more they push them apart. And by pushing them apart, you reduce the amount of density, which reduces the weight or pressure. So in a cold atmosphere, density is going to be higher, so the pressure is going to drop much faster in your vertical than it is in a hot atmosphere. That's why in the tropics, when you go down there and you want to look for the tropopause, you will find that pressure doesn't drop nearly as fast in the vertical, so the tropopause will be higher up. Now, at the pole, where it's very cold, the air is very dense, doesn't take long to reach where the tropopause is. And the 500 millibar is basically halfway through the atmosphere. Oh yeah, and guess what? Moisture, water vapor, is less dense than air. So that means that when you have more water vapor in the air, like in the summertime, the air is actually less dense than it would have been if that had been a very dry air mass. We all feel like it's muggy and it's oppressive when it's hot and humid in the summertime. And the reality is that air is actually lighter than some of the air you experience in the wintertime. Winds converge. The atmosphere is three-dimensional. So say the winds are converging at 500 millibars, 18,000 feet. Well, that's going to push the air down towards the ground. So what that does is compress those molecules down at the ground. You actually wind up with higher pressure at the ground. And the air at the ground is beginning to diverge away from that higher pressure. We've talked about it. Air circulating clockwise in high pressure and the air moving outward. Here is part of the reason why that air has been pushed down. The ideal gas law states that if I know any one of two of the three variables, either pressure, temperature, or density, I can find the other one. It's all it is. It's a means of knowing two variables. I can find a third. So when air pressure expands, when air expands, have you ever released air out of a tire? By accident maybe, or try to bring it down to the right pressure? When you do, the air comes out there quite cold. That is because the air is expanding very rapidly. Now, on the other hand, if you pump air into the tire, I used to have a hand pump, and I would pump bicycle tires up with it. When I did that, that hand pump got very, very hot. That's because I'm heating the air as I pushed it down. The same thing happens in the atmosphere. If air currents rise, they're going to cool because they're expanding. If they're sinking, they're going to warm. And here you can actually see if the air is compressed by the atmosphere as it's sinking, its energy is being used on that air. It heats up. If it expands as it's rising and the air does the work, it cools. There are processes in the atmosphere where no heat is exchanged. That is an adiabatic process. So in other words, the air expands, but it doesn't exchange any of that loss of heat with the air around it. And we're going to talk about parcels of air for the next weeks. You're going to get tired of hearing me talk about them. But I want you to understand an air parcel is just something, try to describe a piece of air. Maybe it's 1 meter by 1 meter by 1 meter. Maybe it's 1,000 meters by 1,000 meters. That can be an air parcel. So when it rises up, it doesn't exchange heat with anything around it. If it does rise up and it's dry, we can calculate how fast that air is going to cool because we know it's expanding. And if it's expanding, it's cooling at the rate of 9.8 degrees Celsius per 1,000 meters. So, if you happen to be on some mountains in West Virginia and were to drive up that mountain, say you went up 1,000 feet, you would literally cool from where you started at the base of it by about 5.5 degrees. Obviously, the same is true when you're going back down. You're going to warm. So that is the dry adiabatic lapse rate. Now, the atmosphere is almost never in that state. But there's also the moist adiabatic lapse rate, and we talked about temperatures being influenced by latent heat. Well, if the air gets moist, it releases latent heat when it condenses. So it cannot cool at the same rate as the dry adiabatic lapse rate. So instead of cooling at that rate, it's only cooling at about 6 degrees Celsius per 1,000 meters. So that means if you have a parcel of dry air next to a parcel of warm air, one is going to cool fast, or moist air, we'll say. One's going to cool much faster than the other. So there's going to be a temperature difference that actually develops between those two air parcels. All right. So this week, I wanted to look just quickly. Here's the pressure we've been dealing with. This is 24, and here it is now. Notice that high pressure 24 hours ago over the Midwest, coming in across your area, cold front approaching my area. Now, same cold front way off the coast, that high pressure is over me, a 1041 millibar high. So you would think, oh, well, 1041 millibars. I have really cold air over my house. This morning I got down to 22 degrees, which for here is cold. Not as cold as some of you all are. I saw some single digits in Ohio and West Virginia this morning. And that cold air makes it very dense. So the pressure is actually going to be dropping fairly quickly in the vertical today in your area. There's a very strong low pressure system up here. So this says that because of that, I probably have divergence aloft over me, pushing the air down, which is helping to increase the air pressure. Up here, I have divergence, convergence back over me, excuse me. And I just wanted to show you, we'll take two airports. These are the pressure changes at that airport. Here is Beckley. We're going to select sea level pressure. If it ever lets me. And you'll see a small curve with this distribution. So, oh well. We'll go here a minute. Maybe I can get this to come back up quick. If not, all right. What this is doing is going out to a server out in western United States in Salt Lake City and trying to calculate all this for me. And right now that server is having some issues, I would say. So, but what it wanted to show you is it has a very small pressure change. You can see these. I give you this web page to use in your course this week to try to look at your pressure changes. If it ever gets here, maybe you can look at them quickly. But if not, I just wanted to, really what I'm trying to show you here is that small pressure changes, and in this case, what you would have seen was the pressure dropping as the cold front was approaching your area and rising as it left. And it was a pretty significant rise. That drop in pressure is what related to your precipitation maybe coming through with the cold front. And here you can see it. We had about a 1032 pressure. It dropped off to about a 1018 pressure. So what is that? 14 millibars basically. And now we're back up over 1037 pressure. And now we're beginning to drop as the high has actually come over towards my house more. So you can see the pressure doesn't change a lot in the vertical. In the horizontal, but it can change dramatically. In the vertical, you think about it, 850 millibars is only about 5,000 feet up. So about a mile up, the pressure has dropped 150 to 170 millibars. That's a lot. So we'll be talking about pressure gradients and their influence on things in a little bit. So hope you got a little bit out of this, and please don't hesitate to ask if you have any questions.